All right, hello everyone. You're at the SIG-Testing deep dive. I'm Cole Wagner, and this is Catherine Berry. We're going to talk about a couple different things today. First one being Prow and ProwJobs in particular, and then we're going to talk about kind and Go-forage. So Prow is a Kubernetes CI/CD system. It's pretty modular in the sense that we can trigger jobs of different types and for different purposes. So we can trigger jobs for testing, publishing, building, and we can trigger them in different ways, have them run on different platforms, and report to different sources. So it's very, very flexible for running jobs. And in addition to that, it also provides some GitHub automation. So we can implement slash commands, merge automation, and policy enforcement. And Prow today is used by a number of different companies you can see there. So you might not know what Prow or ProwJobs are, but if you've contributed to the Kubernetes project, you probably have interacted with them in some way or another. So you might have seen comments like these on some of your PRs. These are used to trigger jobs. You may have also seen some of these statuses at the bottom of your PR. These are the results of those jobs being posted. And you may have also clicked through some links and some comments to see the actual job results. This is Kubernetes, so it's actually slightly different than Prow, but it's showing ProwJob results here. So today we're going to be talking about the life of a ProwJob. So from the instance it is born to the time that it goes back into the ground, if that were to happen. So this is a useful way to learn about the different Prow components and kind of see the flow of how Prow works and how we store state in Prow. And it will also kind of explain some of the magic that you see on your Kubernetes PRs. So as I mentioned before, Prow has many different job types, many different ways you can trigger these jobs, many places that they can run, and many ways to report. If I was to talk about them all today, we'd be here forever. So instead, I'll be talking about one of the more common cases, which is probably what you're familiar with on your PRs. And this is a pre-submit job that runs on a PR, and it's triggered by a test all command. It will run as a Kubernetes pod and report its status to GitHub. So this is like I said, this is one of the more common cases that you probably interact with. And I've got these little tabs at the bottom, so you can see kind of the steps that we go through. So the first step is when the event happens on GitHub. So here a test all command has happened, and GitHub sends us a webhook, and it's got some basic data in it, and tells us who sent it, what the comment was, what the issue is, that kind of thing. That webhook then has to make it to our cluster. Here you can see the ingress rule, the service, and the deployment file. The details are not important. It's really just that it's getting piped through to a hook deployment. So all of our webhooks go to a /hook endpoint, and we pipe them down to a hook binary. And here's a little bit of a diagram for that. So you'll see that the hook binary is composed of a bunch of plugins. And these plugins provide different bits of functionality for different use cases, and we can enable them individually. They don't even have to live inside the binary. So the trigger plugin is probably one of the most common plugins, and it reacts to GitHub events that indicate that a ProwJob needs to be created and run. So yeah, in this case, we would react to a /test all command here. I'd like to point out I'll go on a little tangent here to mention that this is a point of integration for a lot of other Prow's functionality. We can handle any sort of GitHub events here. So here's a GitHub event for a PR being merged that would go to the update config plugin, and we'd automatically update config maps associated with files touched by that PR. And here's a /meow command where we find a cat image on the internet for you and give that to your PR. And really anything can be done with this kind of logic. Plugins get this client here, so you can see they can interact with GitHub, Kubernetes, Slack, the owner's files that we have in the repo. So they don't have to provision most of their own tokens or anything. They kind of just get a toolbox that they can do whatever they need to do with. And if you're interested in more plugins that we have available, that link goes to a bunch of the information that we have about plugins that are currently available. So the trigger plugin, though, is the one that's important for this. That's the one that starts the jobs. First thing it does is it looks at your job config and finds all the jobs that it's supposed to trigger. There's kind of a number of mechanisms that indicate if a job should be triggered or not. But that's Trigger's responsibility to evaluate which ones should be triggered. Once it finds jobs that need to be triggered, it creates ProwJobs CRDs to represent these. So this is how we represent a job that is that exists and is running. So we create this CRD, and it starts in the triggered state. You can see there at the bottom. And we stick that in the API server. And this is pretty nice because it means that to represent our job state, we don't need a database or anything. We can just use the etcd server, or the etcd database that's already inside the API server. So that's pretty handy. So now Trigger has created these ProwJob resources and stuck them in the API server. And Plank can come along. And Plank is it's a controller that's responsible for the main lifecycle of the job. So this is the thing that will actually have the job execute. So the way that this works is Plank runs inside of the Prow service cluster. And because all those ProwJobs are in the API server, it's syncing them from the API server and comparing them to the pods that it is seeing in other build clusters. So the other build clusters are where we actually, those are where we're going to run the jobs. And you can see that the pods for those jobs are running in the clusters. And we are essentially trying to synchronize the ProwJobs that we've identified with the pods that exist in the real world. And there's a number of steps that we do to do this. These are kind of the common handling mechanisms. So when we find a ProwJob that doesn't have a pod, we of course need to create the pod for it. When we do that, we might add some init containers to do source code checkout or some sidecar containers to do log and artifact upload. But the core thing is that we are creating a pod to actually execute the job. Then when we see a ProwJob that's running and has a pod that is completed, either in the pass or failed state, the job is completed so we can mark the ProwJob resource as such. And finally, if we see a ProwJob that's completed, Plank doesn't really care because the job is done, so we don't have anything more to do. But if we just stopped there, all these ProwJobs that are completed and all these pods that are completed would just pile up forever. So of course, we need some garbage collection. We clean up completed ProwJobs after 48 hours, and we clean up completed pods after 30 minutes. These these garbage collection limits that we have are pretty strict because we run such a high load. But that being said, jobs upload their results to GCS. So this isn't like you're losing all of your job history when we do our garbage collection. This is just the recent history that Prow is working with. But if you've just uploaded your results into GCS, you haven't really gotten any notification that your job is completed or anything. And you don't want to have to sit there and hit refresh on GCS to find out when your job results are there. So we have mechanisms for reporting job status and completion. And that is mainly achieved through the crier. So crier is a component kind of like Plank, where it sits in the cluster and it's going to listen to ProwJobs. And it listens for changes in any of those ProwJob resources. And when it finds them, it sends them to reporting clients that are responsible for reporting that status to an external source. So one example of this is the GitHub reporter. So when crier detects ProwJob changes, it notifies the GitHub reporter, and the GitHub reporter can leave these kind of statuses on your PR. And this isn't just for job completion. So we're not just reporting pass or fail here, but we can also report when the job changes other states. So when it goes from triggered to running, that kind of thing. If it errors or is aborted, we can also display all of that. But this is this is one of the branching points where we get more functionality. In particular, this is how we get reporting to different sources. So in addition to just reporting to a place like GitHub, we could instead report to Garrett with a comment, or report to PubSub with a PubSub message. So we can have it potentially do all of these if we wanted to. Excuse me. So that provides a lot of ways for ProwJobs to report their status to the outside world. So that's kind of the overview there. You can really do a lot more with ProwJobs because there is so many ways to trigger them. You can trigger them based on time or based on PRs being merged. There's a lot of ways that they can execute as well, so you don't have to necessarily run your job as a Kubernetes pod. You could use the Knative build CRDs, or if you have some terrible reason to, you could run your job on Jenkins using Prow. And you could also, Actually, I'm not sure if we have any more execution platforms right now, but we are adding more soon. So this is a very modular system. And here, just to finish off, is a fun diagram of Prow. May not be to scale, but yeah, there's just the various Prow components kind of acted out with Gophers. Thanks, Ben the Elder, for making this, and congratulations on making it. Yeah, so Katharine's going to take over now.
Okay, so. So, we can use Prow to run our tests, and yet somehow we always still end up with bugs. What are we missing? In an effort to find out, I'm going to look at how we can measure the code coverage from our end-to-end tests that we're running. This work was originally motivated as part of an effort to figure out what conformance tests are actually accomplishing. However, they can also be more broadly interesting and can show that what code is really executed over any given workload, whether that be conformance tests, all the tests, or even running an application. So, the end result looks something like this. These are specifically the results of running the 1.11, 1.12, and current conformance tests, at least as of when that screenshot was taken, against a master build of Kubernetes. This removes the effect of changes in the underlying code and trying to see how test coverage has improved over time. And as you can see, it is improving slightly-ish. We can also send the coverage results to TestGrid, where you can use all your favorite TestGrid features, like seeing infinite history-ish, and also being able to have graphs. You might notice that everything here is passing, even when it says 0. We tried not making everything pass, but this is what happens when we let our lack of coverage count as a failure. It effectively rendered our triage tooling useless by drowning out everything else. We turned this off in fairly short order. So, support for generating these coverage reports landed in Kubernetes a few months ago, and that means that you can use it yourself. Because it's enabled at compile time, though, and no released binaries are built with coverage enabled because of a minor performance hit, and also because there's no reason you would do that, you must build your own Kubernetes to use it. In order to do so, you must use the make-based build system and pass it the kube build with coverage variable, with any value at all. This also works for other build types, including the ones that build in containers. Make release or make quick release or similar will also work fine. Once your instrumented cluster is running, it will periodically write coverage files to each service's local disk. There are a couple of knobs you can tweak here: where the files are written using kube coverage file, and how often they are written using kube coverage interval, which defaults to 5 seconds, which you might think would have a significant performance hit, but actually doesn't, surprisingly. Finally, you need to actually run some workload and then collect your results. Given that some components are in containers, some aren't, and the containers may have access restrictions, retrieving them can be something of a pain. Fortunately, we have some pre-built solutions. If you're happy running tests on a transient GCE cluster, you can use kubetest's dump flag, which will write logs to disk and include the coverage logs as part of that, your local disk, that is. If you don't want to wait 20 minutes for a shell script to construct a cluster, another option is to use Kind, a new project by Ben the Elder that allows you to run a complete cluster in a container. Just build a Kind node using the same build with coverage variable and using the Kind coverage dump script you can find in the Kubernetes test info repo. Creating the cluster takes under a minute, retrieving the results is instant, and you don't need to pay for any of the VMs, because there are none. Another problem that these sorts of coverage measurements can encounter is noise. Aside from the code directly executed by our tests, we're also going to pick up whatever other activity the cluster happened to perform at the same time. We can help mitigate this by running our tests more than once. But running the tests can take a while, so actually doing this might be kind of expensive in both time and money. Fortunately, Kind can help us here by letting us run many clusters on a single machine. Yes, and then we can run our tests against them. Here, for instance, I have 6 Kind clusters running on my desktop. I can even run a complete conformance suite against all of them simultaneously in less time than it would have taken for startup and teardown of a GCE Kubernetes cluster. So once you have your coverage files, you'll want to do something with them. We built a tool called Go-forage to make the coverage files useful, particularly focusing on manipulation necessary to deal with Kubernetes coverage files here. And we have this lovely logo, which was also drawn by Ben the Elder. So congratulations for having so many parts of this presentation. The first of these tasks that Go-forage solves is merging the coverage files, which is useful when you need to merge files from multiple instances of services, such as, for instance, a multi-node cluster that you just tested, and also to merge coverage from different services into a single coverage file, so that you can see the overall coverage, including any shared code they might have. We have diff functionality, which calculates the difference between two coverage files taken from the same binary or merged set of binaries, and shows you only what was covered between them, which is useful when you need to which is useful in order to find out what was actually covered between two dumps taken. So if you take one before your workload and one after your workload, then you don't actually need to, or rather, then you can exclude the code executed during cluster up, for instance. We have aggregation, which is used when you're running a lot of the same files. When you run the same test repeatedly and want to see how many of those actually covered the same code, which enables you to reduce the noise, as like using that 6-kind setup I had before. And we have Go-forage JUnit and a Go-forage HTML, which will generate a JUnit file, which is useful if you want to dump it into TestGrid or some other tool that consumes those, and if auto-generates a browsable version of your coverage directly. All of these are using standard Go coverage files, so any other coverage tooling for Go will work as well, whether that be something like an online service or indeed the built-in Go tool cover command. And finally, if you're interested in the results but don't actually want to run it yourself, we run them in CI ourselves on our Prow instance cluster. So you can see here we have the conformance and all the tests, with the coverage from the conformance tests being at 29%, and the coverage from all of our tests, of which there are many more, being 35%. So there is maybe some room for some improvement here. So, how does all of this work? Well, Go has some built-in support for generating coverage reports for unit tests. So, what if I told you that we could just make Kubernetes a distributed system of unit tests? So the backbone of this approach is, as with all things Kubernetes, a terrifying and yet completely unavoidable pile of bash. So let's take a look at exactly what the bash does to pull this off. So the first thing we need to do is create some unit tests that we're going to run. In this case, our unit tests are unusual in that they don't contain any tests, and also in that they immediately invoke the original entry point. As you might guess from the name we're passing into init coverage there, they're also code generated by a bash script. The best way to write your Go code. When coverage is enabled, instead of building the normal way, the build system generates one of these fake unit tests, and then uses go-test to generate an executable for this unit test that was formerly a Kubernetes program without immediately running it, because then your build process would take forever. And then, before we invoke the original entry point, our fake unit test first passes a fake command line in order to configure the Go coverage support, and then sets up the coverage dumps. This sort of command line hackery is not unusual in Kubernetes. We actually do the same thing everywhere to deal with glogs behavior. So this now happens repeatedly in these setups. And then finally, we have this periodic flushing function which gets called at the end and periodically in the middle. This features even more hacks. We first create an empty suite of unit tests, then we construct a unit testing platform that does nothing, then we call a pseudo-private function from the Go testing framework to run our non-existent tests. The end result of all of this is a current coverage being written to disk ready to be collected by some other process. Amazingly, this all actually works. So to summarize, this works via unavoidably complicated bash, code generation of unit tests that don't test anything, also in bash, forcing a Go to pass fake command lines in order to convince it we did something, and then creating and running an empty unit test suite every 5 seconds. It's all fine, it all works. Everything here is totally reasonable. And that is about it. So, yeah. You have some closing remarks, I believe.
Yeah, if anybody wants to get involved with SIG-Testing or Prow, pretty much almost all the tools that we've talked about have a folder under the Kubernetes test info repo. And the SIG-Testing Slack channel is a great place to reach out if you don't know how you want to get started. Yeah, any questions?
How long did it take you to make that graphic with me?
The question was how long it took to make a graphic of SpiffXP. The answer is about half an hour, because we're really bad at using slides. It was time well spent, though. Anyone else?
Is it SIG-Testing that's responsible for maintaining the Kubernetes cluster that Prow's running in, or is that?
So currently it is a kind of a subset of SIG-Testing, because currently only Googlers have access to the cluster. We are in the process of switching that over to CNCF-funded architecture so that any contributor can be part of the team that is managing that. If you're interested in that, I believe there's a Kate's Infra team working group. So there's a Slack channel for that.
You?
Can you use open source test grid?
Michelle? Yeah, we'd love to open source test grid. If you want test grid open sourced, there is a GitHub issue that you should post on and say that you want test grid open sourced.
And
Michelle
explain why.
can help with that too. Yes. We very much would like to do that though. That's kind of the last piece of our ecosystem that isn't quite open sourced yet.
Also, it's issue number 10409. Tested from 10409.
Thanks.
Could Kine be used for end-to-end testing as well, or is it just for unit testing?
Kine can be used for end-to-end testing, and indeed we do run some end-to-end tests on it, and they all work. So it is a design goal, and it's a good idea to do that. Just run your tests against it, like any other cluster.
Do you know of any not Kubernetes projects who use Prow for their testing?
Yeah, so I think that was one of the early slides that I had.
The second slide.
Yeah, no worries. Yeah, so here's some logos. But yeah, there's a number of other organizations that use Prow. I think some of the biggest ones are OpenShift and JetStack, and probably Istio and Native after that, Knative.
Those are all Kubernetes projects.
Yes, so the Linux kernel mailing list is actually starting to use Prow. Yeah, there's other people out there that are using it. That's also kind of Kubernetes though, right? So yeah, I mean, if you use Kubernetes, Prow is kind of an obvious choice because it runs on Kubernetes and you're familiar with it, so it's easy for you to deploy. So there's kind of a lot of synergy there, but there are some other people outside of the Kubernetes community using it, yes.
So you have, you computed the overall test coverage numbers for the E2E tests and performance tests. Do you have combined numbers on the unit integration tests as well? Or
I do not have combined numbers for unit integration tests, but I do know that the unit test coverage, which we don't formally measure or collect anywhere, is currently 53% for Kubernetes.
If only there was somebody
somebody in charge of build and release who could actually write a job to collect all of that. It could work for Google.
You can actually derive value at the end-to-end coverage. Generally, end-to-end, you're not really targeting large coverage. It's usually more, integration across multiple components. Really good shallow coverage.
So we are attempting to use the end-to-end integration test coverage in order to try and determine what sorts of behaviors our end-to-end tests are actually exercising. So while we aren't trying to get those to 100%, which would be basically impossible for an integration test, we are trying to see which areas are completely omitted but probably shouldn't be.
I think a lot of the utility is when you dial down into the specific packages when you're looking at that scale.